Hello, everyone. So this is the first installment of my 3 or 4 parts lecture series for functions, limits, and continuity. And these 3 words, function, limits, continuity, are very important on the study of calculus. And we shall start our lecture by defining a functions. And it's a very common knowledge for us that the function assigns rule to describe how a certain quantity depends on the values of another variables. And in particular, the equation of the line y equals mx plus b sets the relationship between the variables x and y, and this relationship can be thought as a correspondence from a set x, a real number x, and to a set y, a real number of y. So technically, we define a function to be the set of ordered pairs xy in which no two distinct ordered pairs have the same first number, and this real number x is what we call the domain, and this set of real number y is called the range. And small letters f, g, and h denotes a function unless stated otherwise, and when written or when expressed in terms of the variable x, we let f of x, g of x, h of x to denote a function. So for instance, if we let f be defined by f of x equals to x minus 1, then it can be observed that f is a function since when x is replaced by any number or any real number, then we can have exactly one value of y. Okay, for instance, when x is -3, y equals -7. When x is -2, y is -5. When x is -3 or -1, f of x is -3. When x is 0, f of x is -1. When x is 1, we have 1. When x is 2, we have 3. And finally, when x is 3, we have 5. And this set containing -3, -2, -1, 0, 1, 2, and 3 is the domain, and -7, -5, -3, -1, 1, 3, and 5 is called the range. And you will notice that no two or more ordered pairs have the same first number. So the relation f defined by f of x equals 2x minus 1 can be thought as a functions. And if we let f be defined by the circle x squared plus y squared equals 9, then you will notice that when x is 0, when x is replaced by 0, you will have y equals 3 and -3. So we have the set of ordered pairs 0, 3, and 0, -3. And based on our definitions, a function is a set of ordered pairs wherein no two or more ordered pairs have the same first number. So we have here 0 and another 0. So this is 0, 3, this is 0, -3. So x squared plus y squared equals 9 cannot be thought as a function, but it's a relation. We set rules for the variables x and y. Similarly, the ordered pairs 3, 0, -3, 0, 1, 2 square root of 2, and 1, -2 square root of 2 can also be obtained from the given circle. Okay, and how do we define or how do we identify whether a relation is a function or not? Okay, when a graph is given, then we can easily identify a relation whether it's a function or not through a vertical line test. So here is the idea. So what are we going to do is to draw vertical lines that will pass through the graph of the relation, okay? And if the vertical line passes through exactly 2 or more points on the curve, then that is not a function. And you will notice that when I draw vertical lines over the circle, x squared plus y squared equals 9, the vertical line passes through exactly 2 points. So that confirms that the circle is not a function. However, if we draw vertical lines over this curve, then you will notice that there is exactly 1 point on the curve by which the vertical line passes through. So which means this relation or this curve is a function. And another way to do it is by mapping. Okay, so let us consider the relation f of x equals to x minus 1. And we know that when x is -3, f of x is -7, and -2 maps to -5, -1 maps to -3, 0 maps to -1s, 1 maps to 1, 2 maps to 3, and 3 maps to 5. And you will notice that for every value of x, there is exactly one value of y mapped to it. So therefore, we have a one-to-one correspondence or one-to-one mapping. So therefore, we can thought a one-to-one correspondence as a function. Okay, going back with our circle, x squared plus y squared equals 9. Earlier, we have identified that the circle is not a function but a relation, of course. So by mapping, so you will observe that -3 maps to 0. When x is 0, it will be mapped to -3 and +3. When x is 1, then we have -2 square root of 2 and 2 square root of 2. And when x is 3, we have 0. So you will notice that there is exactly one value of x mapped to two values of our y. Okay, there is one is mapped to two values of y, and therefore we have one to many correspondence, and therefore the one to many mapping cannot be thought as a function. And another one we have here, g of x equals x squared plus 1. And then you will notice that when x is -3, y is -10, or g of x is -10, or +10, sorry. And when x is -2, we have 5, -1 maps to 2, 0 maps to 1. Okay, so the idea is I am just replacing x by these numbers, and then we obtain g of x. So when x is replaced by 1, so 1 squared plus 1, so we have 2. When x is 2, we have 5. And when x is 3, g of x is 10. And you will notice that there are two values of x mapped to only one value of g of x. So again, say 3 and -3 are both mapped to 10. And therefore, we have many-to-one mapping or many-to-one correspondence. And the many-to-one mapping or many-to-one correspondence can be thought as a function. Right? How to evaluate a function? One easiest way to evaluate a function is by a straightforward substitution. For instance, if we let f be a function defined by f of x equals x squared minus 2x plus 3, and if we want to get this value, say f of 2, f of 1/2, f of -1, f of 2x, and f of x plus h, and then we can do a straightforward substitution. For f of 2, you will just be replacing x by 2. So you have 2 square minus 2 times 2 plus 3, and you obtain 3. So f of 2 equals 3. For letter B, if we replace x by 1/2, so we have f of 1/2 equals 1/2 squared minus 2 times 1/2 plus 3. So 1/2 squared is 1/4, and -2 times 1/2 is -1, and then plus 3. And then you have 9/4 to be our f of 1/2. And then f of 2x, so sorry, f of -1. So again, you replace x by -1. So -1 square minus 2 times -1 plus 3, and that will give you +6. This is 1, and this is 2. So 1 plus 2 is 3, plus 3, you have 6. For f of 2x, so here you replace x by 2x. So you have the quantity 2x squared minus 2 times 2x plus 3. Then 2x squared is 4x squared minus 2 times 2x is 4x plus 3. So f of 2x is given by 4x squared minus 4x plus 3. And then finally, if we want to evaluate f of x plus h, so this time we will be replacing x by x plus h. So you have the quantity x plus h squared minus 2 times the quantity x plus h plus 3. And then simplifying this algebraically, we have x squared plus 2xh plus h squared. That's the square of x plus h, the square of the first, plus twice the product of the first and the second, plus square of the second. And then you introduce -2 each term here. So you have -2x minus 2h plus 3. And I think we can no longer combine anything here. So the final answer would have been equal to x squared plus 2xh plus h squared minus 2x minus 2h plus 3. Okay? How to find the domain and the range? Again, the domain and the range of the function is also an important characteristic of a function. Again, the domain is the set of the real number x, and the range is the set of the real number y. Okay? And then by definition, the set of all admissible values of x is called the domain, and then the set of all permissible values of y is called the range of the function. And say we have a function f of x equals 2x plus 3. So what are you going to do is to identify what are those values of x that can be used to replace x here. What are those real numbers that can be used to replace x here? Can x be replaced by positive number? Can x be replaced by 0? Can x be replaced by negative number, such that the result is still defined? Okay, and it can be thought that you can replace x by any number on the set of real numbers. So the domain of this function is the set containing x such that x is an element of real numbers. Or in interval notation, we use this negative, the open interval negative infinity to positive infinity. Now, for the range, what are you going to ask for is, after replacing x by any number on this interval, what happened to your f of x? If I replace x by negative number, what happened to your f of x? If I replace x by 0, how do you characterize f of x? If x is replaced by positive number, then how do you describe your f of x? And replacing x by any number on this interval, then we can say that the range of this function is the set of real numbers, or all reals, or in interval notation, that is negative infinity to positive infinity. Okay. Okay, say if we let g be a function defined by g of x equals square root of x, and then we have here a square root of x, and then we know that if a number is written inside the square root, then this number x cannot be negative. Okay, so that's an important consideration. So we know that the domain of this function is the set of all non-negative real numbers, or the set the set containing 0 to positive infinity. And in interval notation, this is read as the closed open interval of 0 to positive infinity. And when x is replaced by any number on this interval, we say that the range of this function is the set containing 0 to positive infinity, including 0. Okay, if we want to trace this curve, then we can have this. So your g of x equals square root of x is this represented by this graph, or by this curve. Okay, and you will notice that the domain of this function is from 0 to positive infinity, and then the range is from 0 to positive infinity. Okay, another one. Say, let f be a function defined by f of x equals 2 over x. And if we want to find its domain and range, again, this is a rational function of the form p of x over q of x. So we know that whenever you were given a fraction, the denominator should not be equal to 0. Why? Because when the denominator is 0, then the function f of x is undefined, because we are taught that dividing by 0 is or is undefined. Okay, so which means we will be excluding 0 on the set of our domain. So the domain of this function is the interval negative infinity to 0 union the interval 0 to positive infinity, or this is the same as the set of real numbers except 0. Okay, now for the range, so we have negative infinity to 0 union 0 to positive infinity. Okay, so this is how we draw the curve. So you know that x cannot be 0, okay, and y cannot be 0. Okay, so that is the reason why the curve f of x equals 2 over x is asymptotic with respect to the x-axis, and also asymptotic with respect to the y-axis. When we say asymptotic, it means that the curve or the graph of that function will just go nearer and nearer to x-axis, but will never touch the x-axis. So that is what I mean when I say asymptotic with respect to the x-axis. So when it is asymptotic with respect to the y-axis, the behavior of the curve gets nearer and nearer, closer and closer to the y-axis, but will never cross the y-axis. Okay, And that is what you call the horizontal asymptote, okay? And the y-axis is the vertical asymptote for this particular function f of x equals 2 over x. Okay, another one. Say we modify the given function. We now let f be defined by f of x equals 1 over x squared. So this time, the denominator x squared. So how we may replace x? So can we replace x by negative number? So obviously yes, because when x is replaced by negative number, the result is still defined. Now, can we replace x by positive number? Of course, yes, because when x is replaced by positive number, still the function f1 over x squared is still defined. Now, when x is replaced by 0, so this will become 1 over 0. So the function is no longer defined at x equals 0. So we want to trace it. So as you notice that when x is approaching positive, a very, very large number, the value of y diminish or the value of y decreases and it gets closer and closer to 0. And as x approaches 0, as the value of x gets closer and closer to 0, okay, the value of your f of x gets larger and larger, approaching positive infinity. And since y cannot be negative, because if we replace x by any number here, positive x or negative number, then still the result will become positive because of this x squared, because of that square. So the other part of the curve is this, okay? And as x approaches a very large number on the left side, again, y approaches x, and as x gets closer and closer to 0 from the left, your y gets larger and larger, approaching positive infinity. And again, this is your horizontal asymptote, and then this one is your vertical asymptote. Okay, and then the domain of this function, as you can notice, so that's the set of real numbers except 0, or the interval negative infinity to 0, union the open interval 0 to positive infinity. And as you can notice, there's no trace of the curve on this portion of the coordinate system. Therefore, the range is the set of non-negative real numbers, or the containing 0 to positive infinity. Okay. For the graph of the function, okay, we define the graph of the function as the set of all points xy in the plane r square, for which xy is an ordered pair in F, or that's the locus of points. Okay. Okay, so to easily trace the behavior of to easily trace the graph of a function, I identify some 5 basic steps. The first one is you identify the domain and range and the properties of the function. The second one is to choose the suitable values of x from the domain of a function and solve for its corresponding value of y. Third, determine the behavior of x and y. And fourth, plot the points x and y on xy on the plane. And 5, smoothly trace the curve. Okay, let's try some examples. Say we want to sketch the graph of f of x equals 2x plus 3. We know that the function f of x equals 2x plus 3 will give us a line. Okay, and to trace or to sketch a line, we might use the rise over run technique. So here we will be getting the slope of the line, and then we will be using the rise over run. When we say rise, that's the going up and going down, and run going to the left or to the right. Okay, so when the slope m is positive, we can go up, then right, or down, or then left. And then when the slope m is negative, we can go up, then left, then go down, then right. Okay, so we will be writing f of x equals to x plus 3 of the form y equals to x plus b, and we notice that the slope is equal to 2. Okay, m equals to 2, positive 2, that's positive 2. So 2 can be written of the form 2 over 1. So that's 2 unit rise and 1 unit run, or negative 2 over negative 1. So I can go 2 units down or 1 unit left, or 2 units up and 1 unit right. Okay, So how do we start tracing this curve? So we might start at the intercept when x is 0, so y equals 3. So we will be starting at 3, 0, 3. Okay, and then so from here, can I just go down and left? Okay, that's the convenient here. So I will go 2 units down and then 1 unit to the left. Okay, so I might have a point somewhere there, and then since a line is determined by at least 2 points, then I can now draw my line. So this is the line f of x equals to x plus 3. And another way to to determine the domain of this function is you look for the values of x by which the graph will be passing through, and the domain of this function is negative infinity to positive infinity, and then the range is negative infinity to positive infinity, or the set of real numbers. And another way to sketch the graph of this function is by applying the intercept techniques. So here we will be getting the x-intercept. The x-intercept is the point on the x-axis by which the graph will pass through. And here we will be setting y equals 0. So when y equals 0, we solve x equal to negative 3 halves. So we have an ordered pair, negative 3 halves, 0 to be the point on this line. And then the y-intercept, sorry, that's negative 3 halves 0. And then after which we will be looking for the y-intercept. And the y-intercept is the point on the y-axis by which the graph passes through. And here, if for the x-intercept, we let y equal 0. So for the y-intercept, we will set x equals 0, and then we look for y. So when x is replaced by 0, so 2 times 0 is 0 plus 3, so that is equal to 3. So y equals 3. So you have 0, 3. And then we locate that here, 0, 3. And again, since a line is determined by at least 2 points, and then we can now easily trace the line 2x plus 3. Okay, another one. Say we sketch the graph of f of x equals the square root of 25 minus x squared. Okay, I will just be replacing f of x by y. Okay, so I now have y equals the square root of 25 minus x squared. And this equation can be thought as y squared equals 25 minus x squared. If you square both sides of this equation, then you have y squared, and then the square root will be avoided. So you only have 25 minus x squared on the right side. Okay, and then manipulating this equation, that led us to x squared plus y squared equals 5 squared. And recalling the properties of a conic section, so x squared plus y squared equals 5 square determines a circle with radius equal to 5 and whose center is located at 0, 0. Again, so this is x squared plus y squared equals 5 squared, and this is a circle with center at the origin 0, 0. And the radius equal to 5. Okay, so this is 5, 0. So from the center, this is the center 0, 0. From the center, you count 5 units. 1, 2, 3, 4, 5. So since our radius is equal to 5, and then from the center, you go 5 units here, 5 units to the left, and then 5 units down. And then we can now easily trace the circle x squared plus y squared equals 5 squared. So however, what we are looking for is the function f of x equals 25 minus x squared. Okay, so we notice that the domain of this function is the closed interval negative 5 to 5. Okay, and then the range is also negative 5 to 5. Okay, so however, what we only need to look for is the function f of x equals to the square root of 25 minus x squared. So the idea is I'll be dividing this into 2 semicircles. We have this, okay? So this is now your y equals the square root of 25 minus x squared. Then again, by the vertical line test, we will notice that this function y equals the square root of 25 minus x squared is really a function. And then what about the semicircle below the x-axis? Okay, By the way, the domain of this function is the interval -5 to 5, and then the range is from 0 to 5. Okay. And then what about the semicircle below the x-axis? So the equation would have been equal to y equals negative, since we are now on the negative y-axis. So negative the square root of 25 minus x squared. And again, the domain of this function is the closed interval -5 to 5, and then the range is from -5 to 0. Okay, let's play along with this circle x squared plus y squared equals 25. Okay, again, this is the circle, and if I divide this into two semicircles, the one on the left side and the right side of the y-axis. So this semicircle is the equation x equals 25, the square root of 25, sorry, minus y squared. And this cannot be taught as a function since by vertical line test, the vertical line passes through exactly 2 points on the curve. And again, the one written, the one drawn on the uh, left side of the y-axis is the curve x equals negative the square root of 25 minus y squared. And then the domain of this function is from the closed interval -5 to 0, and then the range is the closed interval -5 to 5. Okay. Okay, another one. We sketch the graph f of x equals the square root of x squared minus 4. And again, I will just replace f of x by y. So I now have y equals the square root of x squared minus 4. And then again, manipulating this equation, squaring both sides, I have now y squared equals x squared minus 4. And then eventually, I can have x squared minus y squared equals positive 4. And again, recalling the properties of the conics, this is now a hyperbola with center at 0, 0, with minor and major axis equal to 2. Okay? So this is negative to 0, this is to 0, and then we can now easily draw our hyperbola. Y squared equals x squared minus 4, or x squared minus y squared equals 4. Okay, and again, what we are looking for is the function f of x equals the square root of x squared minus 4. Again, the hyperbola x squared minus y squared equals 4 cannot be taught as a function. Again, by vertical line test, it does not qualifies to be a function. Okay, and then again, what we only need to look for is the half of the hyperbola. Okay. So this is now your f of x equals the square root of x squared minus 4. And then the domain of this function is the interval, the open and closed interval -infinity to -2 union, the closed open interval to positive infinity. And you will notice that the range of this function is from 0 going to positive infinity. Okay. Another one. Say we sketch the graph of the function f of x equals 2x squared over 25 minus x squared. Again, this is a rational function of the form p of x over q of x. So we should set this denominator 25 minus x squared not to be equal to 0. So we have 25 minus x squared not equal to 0. And then factoring this difference of two squares. So you have 5 minus x and 5 plus x not equal to 0. So you obtain x equals 5 and x equals -5. So we can say that x cannot be 5 or -5. Okay? And then you will notice that the domain of this function is any number, any real number except 5 or -5. So in interval notation, we write the open interval -infinity to -5, union -5 to 5, union 5 to positive infinity. And we will verify that the range of this function is the interval -infinity to -2, union close open interval 0 to positive infinity. Okay? So this is your x equals -5. So that is considered our vertical asymptote because x cannot be -5. Another one is on the right side, x equals 5, and this is another vertical asymptote. Okay, since x cannot be 5. And then, by the way, another term for vertical asymptote is the line discontinuity or infinite discontinuity. Okay, one more. It's line discontinuity or infinite discontinuity. Okay, so what about y equals -2? So this one is our horizontal asymptote since f of x cannot be -2, and how we obtain and how do we obtain -2? So by getting the coefficients of x squared on the numerator and x squared on the denominator, so that's 2 over -1, so you have y equals -2. So why do we need to do that? One particular condition that we are going to do it is if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote are the coefficients of those two terms with equal degrees. So in this case, so this is 2x squared over -x squared. So the coefficients are 2 and -1. So 2 over -1 is -2. So the line y equals -2 is our horizontal asymptote. And then we might trace this curve. Okay. So this is the behavior of the curve. And you will notice that the the curve to x squared over 25 minus x squared, as x approaches a very large number to the left, y gets closer and closer to -2. And similarly, when x gets closer and closer to -5, y approaches -infinity. On the other side, as x gets larger and larger, going to positive infinity, y gets smaller and smaller, nearly approaching -2. And similarly, when x gets closer and closer to -5, your y decreases, going to -infinity. And other part of the curve is this parabola. Okay, you will notice that when x is 0, obviously y is also equal to 0. And this is the lowest point of this part of the curve. Okay. Sketch the graph of the function f of x equals 1 over x squared minus 16. Again, taking the idea that the denominator should not be equal to 0, so we know that x cannot be -4 or +4. Okay. So this is your x equals -4, your x equals 4, and then these two are the vertical asymptotes or the infinite discontinuity. And then the line y equals 0 is your horizontal asymptote. Where do we get this y equals 0? You will notice now that the numerator is a constant 1. Okay? So this is 1. So therefore, the degree of the numerator, which is 0, is less than the degree of the denominator. Then the x-axis is horizontal asymptote. Again, earlier, you notice that on our previous example, that's 2x squared over 25 minus x squared. The degree of the numerator, by the way, the degree is the highest power or the highest exponent on the numerator and denominator. So on our previous example, 2x squared over 25 minus x squared, you notice that the degree of the numerator 2 is equal to the degree of the denominator. That's the reason why the horizontal asymptote is y equals -2. In our next example, the degree of the numerator is 0 and the degree of the denominator is 2. And the degree of the numerator is less than the degree of the denominator. So therefore, the x-axis is a horizontal asymptote. Okay, and then we might trace the curve. Okay, and the domain of this function is the set of real number except plus or minus 4. And then the range is the open and closed interval -infinity to -1 over 16 union the open interval 0 to positive infinity. And that is confirmed by the graph, since there are part of the graph traced on the negative y axis. So you start at -infinity, going to this point, and this is your negative 1 over 16. How do we get that negative 1 over 16? Obviously, when x is 0, when this is 0, so you have 1 over negative 16. So 0, negative 1 over 16. I think this would be the last. We sketch the graph of the function f of x equals x squared minus 9 over x plus 3. Okay. Again, this is a rational function, so we might say that x plus 3 cannot be equal to 0. Okay. So we say that x cannot be negative 3. Okay. Because when x is negative 3, the denominator will become 0. Okay. However, you notice that x squared minus 9 all over x plus 3 is not in lowest term. Okay? Why? Because we can factor out x squared minus 9 of this form. X plus 3, x minus 3. And then all over x plus 3. So you can now cancel this out. So we only left with x minus 3. So f of x can now be thought as x minus 3. So this is again a line whose graph. Okay, this is the graph of the line y equals x minus 3. However, we identified earlier that x cannot be negative 3. So x cannot be, negative 3 cannot be used to replace x here. So we might have a hole there, okay? And this one is called the point discontinuity. So when x is negative 3, so y is negative 6. So from here, you replace x by negative 3. So y equals negative 3 minus 3, and that leads you to y equals negative 6. Since x cannot be negative 3, therefore y equals negative 6. That is the reason why we have a hole here. Okay? So again, this is what we call the point discontinuity. And again, the domain of this function is the set of real numbers except negative 3. And then the range is the set of real number except negative 6. Okay. I have mentioned earlier the asymptotes, and this is a basic definition of an asymptotes. How do you determine whether a line is a vertical asymptote or a horizontal asymptote? Suppose that f of x equals p of x over q of x is a rational function in lowest terms, meaning the numerator and denominator do not have any common factors. And a is some real number where q of x is not equal to 0, then the vertical line x equals a is a vertical asymptote of the graph of f if as x approaches a, then the absolute value of f of x approaches infinity. Okay? And the horizontal line y equals a is a horizontal asymptote of the graph of f if as the absolute value of x approaches positive infinity, then f of x approaches a. Okay. Suppose that the rational function f of x equals p of x over q of x, and where p of x is written of this form, a sub n x raised to n plus a sub n minus 1 x raised to n minus 1 running until a sub 1 x plus a sub 0. And q of x is written of the form b sub m x raised to m plus b sub m minus 1 x raised to m minus 1 running until b sub 1 x plus b sub 0. And the where q of x is not equal to 0 and that p of x over q of x is in lowest terms. And here are the qualification of to become an asymptote. Okay. If q of a equals 0, then x equals a is a vertical asymptote. Okay, next. If n is less than m, meaning the degree of the numerator is less than the degree of the denominator, then the x-axis is horizontal asymptote. Next, if n equals m, then the horizontal asymptote is the line y equals a sub n over b sub n, meaning we just get the coefficient of x to the n and x to the m. So that's a sub n over b sub m. And if n is greater than m, then the graph of f has no horizontal asymptote, meaning if the degree of the numerator is larger than the degree of the denominator, then the graph of f has no horizontal asymptote. And that is observed from our previous examples. Okay, another one. Say f of x equals x squared plus 5x plus 10 over 2x plus 6. We will be determining whether this function has horizontal asymptote or vertical asymptote. Okay. So we let p of x equals x squared plus 5x plus 10 and q of x equals 2x plus 6. And we notice that the degree of p of x n equals 2 and that the degree of q of x m equals 1. So that's the highest power here, x squared plus 5x plus 10. The highest exponent is 2, so that's the degree. And then for 2x plus 6, the highest power is equal to 1. Okay? So since the degree of the numerator, n, is larger than the degree of the denominator, 2 is greater than 1, therefore this function has no horizontal asymptote. Okay? And for the vertical asymptote, we will be getting 2x plus 6 and we equate it to 0. So we'll say x equals negative 3. So the line x equals negative 3 is a vertical asymptote. Now, say f of x equals p of x over q of x can be reduced of the form g of x plus r of x over q of x. This g of x plus r of x q of x can be obtained if you divide p of x over q of x. When are you going to divide the fraction, or when are you going to divide p of x by q of x? That is when the degree of p of x is greater than or equal to the degree of q of x. So when you divide p of x by q of x, you have a quotient plus remainder over divisor. So q of x is the quotient and r of x is the remainder. Okay? And if this g of x is a line of the form mx plus b, okay, if this g of x can be written of this form mx plus b, then the line y equals mx plus b is an oblique asymptote. So you now have vertical asymptote, an oblique asymptote, and horizontal asymptote. Okay? So obviously this function f of x equals x squared plus 5x plus 10 all over 2x plus 6 has a vertical asymptote, and that is the line x equals negative 3. However, it has no horizontal asymptote. So what are we going to do now is to identify whether this function has an oblique asymptote. Okay? So what are we going to do is we will be dividing this x squared plus 5x plus 10 by 2x plus 6. By long method of division, okay, I used long method of division here. So we have when x squared plus 5x plus 10 is divided by 2x plus 6, the quotient is 1/2 x plus 1, and then the remainder is 4. Okay, so we now have f of x can be written as 1/2 x plus 1 plus 4 all over 2x plus 6. And then since this 1/2 x plus 1 is a line of the form y equals mx plus b, therefore the line y equals 1/2 x plus 1 is an oblique asymptote. Okay, so we recall that the vertical asymptote of this function is the line x equals negative 3. And then we trace this curve. Okay, so this is the line x equals negative 3. And then obviously again there is no horizontal asymptote, but we have an oblique asymptote of the form y equals 1/2 x plus 1. And this is the line y equals 1/2 x plus 1. Okay, so we can now easily trace the graph x squared plus 5x plus 10 over 2x plus 6. And obviously, it will not pass through these lines, x equals negative 3 and y equals 1/2 x plus 1. And we will assume the values of x. Say when x is 0, the question now is, will this function passes through the y-axis? So when x is 0, 0, 0, and x is 0, so you have 10 over 6. 10 over 6, that's approximately 5/3. So that's 1.67. So we locate that 0, 1.67, and we find it there. Okay, that's 1.67. And then we can now easily trace the curve, okay? And you will notice that since this is an asymptote, the behavior of this curve will just get closer and closer to this line, but will never pass through. And then it will also get closer and closer to x equals -3 and will never pass through. And this curve will have a reflection over this side of the Cartesian coordinate system. Okay, and that completes the graph f of x equals x squared plus 5x plus 10 all over 2x plus 6. And that's it. That's it for now. And on our next video, just keep on tuning into my channel. I'll be presenting to you how to perform operations on functions and the different types of functions. And that's it for now. And I'll see you next on my on my next videos. Goodbye.